Uh, Welcome back. We have some physiological experiments to go through. The first one of which is a qualitative test. That is demonstration of the presence of a carbohydrate in a sample solution. We have taken the carbohydrate sample as glucose solution. We know what it is actually. We will test for its presence, quality only, not quantity. Working principle. All carbohydrates are Mollis positive macromolecules. There is a reagent, Mollis reagent. And when Mollis reagent is added to a carbohydrate solution, any carbohydrate, say for example, we have taken glucose to glucose solution, second well, and then 1 to 2 drops of concentrated sulfuric acid is rolled down along the side of the test tube gently. A purple blue ring will develop at the interface of the two liquids. This indicates the presence of a carbohydrate, whether be it glucose, the fructose, or starch, or any other carbohydrate. All carbohydrates are Mollis test positive macromolecules. For this we require, it's a very simple experiment, no technicality. For this we require test tubes. First of all, test sample, then test tubes, Mollis reagent, and concentrated sulfuric acid. Mollis reagent is available commercially. There is nothing to worry, but one needs to know its composition. It contains alpha-naphthol. A phenol, alpha-naphthol is a phenol. It contains alpha-naphthol. It is dissolved in absolute alcohol. The concentration is made to 5%. That is, 5 grams of alpha-naphthol is dissolved in 100 ml of absolute alcohol. This makes a Mollis reagent. That is 5% alpha-naphthol solution. Sorry. Then proceeding. 2 drops of Mollis reagent is added to 2 ml of the sample solution in a test tube and second well to mix. Ma'am, 2 ml of, okay, you have had the result already.
I can use it.
Okay, that's it. So you take the sample solution, 2 ml of sample solution in a test tube. To the sample solution, you add 2 to 3 drops of 2 drops of the Mollis reagent. Mollis reagent, as I have already mentioned, is commercially available in the market. You need not have to worry about its preparation. At the higher secondary level, we advise to go for the Mollis reagent from the market, not prepare it, because it takes a lot of time. Alpha-naphthol, absolute alcohol, those two things have to be mixed. Maybe it won't materialize. Anyway, we always advise to go for reagents from the local market. Commercially, everything is available. So to it, you have added Mollis reagent, you set it well. Then you incline the test tube, roll down 2 drops of concentrated sulfuric acid along the inner side of the test tube. So the sulfuric acid drops will roll down and will come in contact with the solution beneath. Immediately, a ring, bluish purple ring will be formed at the interface, at the junction of the two liquids. If it is formed, then it's very simple. you confirm the presence of a carbohydrate. That's it. Very simple experiment. The next experiment is demonstration of reducing property of glucose. Most of the sugars are second experiment. Most of the sugars are reducing. For example, glucose and fructose, mannose, galactose, lactose, maltose, all these are reducing sugars. But sucrose is not. Why it is not? I'll be telling you a little later. Glucose is reducing. We take glucose as an example always. Glucose is reducing because you know that glucose is derived from an aldehyde. It's an aldose. It is an aldehyde derivative. As an aldehyde derivative, it has an ability to reduce metal ions in solution. Metal ions means the ions which have metals which have variable valencies. For example, copper, silver, etc. These are variable. These can exist in variable valence states. Therefore, this can be reduced by glucose in solution. For this, we use the Benedict's reagent as the reagent. Benedict's reagent has copper sulfate. Copper sulfate as the base chemical. So what happens in this reaction? Copper sulfate that is present in the Benedict solution is a cupric state. Cupric state, 2 plus. Its valency is 2 plus. When it is added to glucose solution and heated for 1 to 2 minutes, the color of the solution, resultant solution, turns brick red and a precipitate is formed. The precipitate indeed is cuprous oxide. So we initially took copper sulfate. The valency was 2 plus cupric sulfate, and now cuprous oxide is formed. The valency is 1 plus. So cupric state is reduced to cuprous state. And secondly, copper sulfate is soluble in water. That was present in soluble form in Benedict's solution. But when it formed a cuprous oxide, it became insoluble. It precipitated out as a brick red color precipitate. So cupric to cuprous is brick red. Look at this. The color of the solution. Look at the color of the solution. The bright brick red color is formed. Okay, this indicates that glucose is a reducing sugar. We knew glucose. It is a known sugar we have taken in the experiment. But anyway, if you take an unknown sugar and taste its reducing property, you can conduct this experiment without knowing the sugar. You can only make a remark whether it is reducing or non-reducing. In glucose, the reducing property lies with the carbon atom 1, first carbon atom. Similarly, if you consider the case of fructose, the reducing property in fructose lies with the second carbon atom, not with the first carbon atom. However, if you consider a disaccharide, namely sucrose, table sugar, it's non-reducing. It doesn't have the ability to reduce metal ions in solution. Why? The two sucrose is made up of two monosaccharides joined together by a glycosidic bond. The two monosaccharides are glucose and fructose. The first carbon atom of glucose joins to the second carbon atom of fructose, such that a glycosidic bond is formed. And the two carbon atoms are reducing carbon atoms. When both the carbon atoms are engaged in the bond formation process, how can it be reducing? It can't be reducing. You hydrolyze it, turn sucrose into glucose and fructose, then test for its reducing ability. It will give you a positive result. The same kind of precipitate, brick red color precipitate, will be formed. Anyway, so this is all about the reducing property. I have already gone through it. The next, presence of starch, determination of the presence of starch in a sample solution. All carbohydrates exhibit, as I have already discussed, all carbohydrates exhibit Mollis test. They are positive with Mollis test. Secondly, we take starch solution. First, we have to conduct Mollis test. Once we confirm that it's a carbohydrate, then we go for iodine test. If both tests are positive, then we confirm the presence of starch in a given solution. Please. Mollis test. Don't say it. No. Then roll down sulfuric acid. Yes, you can roll down. Anyway, it's done. The previous one that we did the photograph was better.
Let's go back.
Huh?
Let's go.
Starch. Go through the starch confirmation test. For starch confirmation, we have to go through two tests in succession. The first test, Mollis test, we confirm the presence of a carbohydrate, and the next test is iodine test. This will confirm the presence of starch. Yes. First Mollis test. This is intensely blue, black or blue in color. Look at this. This is the consequence of the result of the iodine test. This is the result of the iodine test. We will conduct Mollis test. We have already gone through the Mollis test in the past experiment. Following Mollis test, we undertake this test. Two tests. So starch is confirmed. Next experiment is determination of the presence of protein in a sample solution. For this, we require a test sample, that is egg albumin in a aqueous solution.
Protein.
Get an egg, break the shell, remove the yolk, rest part, the white part is called the albumin. The albumin of an egg is very rich in proteins. It's selected as a source material for proteins. Hence, we have taken egg albumin. We make a solution, any concentration, it doesn't matter. Because we are not testing its quantity, we are testing its quality. Whether protein is present in the sample or not. That's all. For this, we require a test sample, that is egg albumin solution. Then test tube holder, spirit lamp, and a reagent. very unique reagent, biurate reagent. Biurate reagent contains sodium hydroxide and hydrated copper sulfate. In addition, Rochelle salt is also present in biurate reagent. Sodium potassium tartrate is also present in. Yeah, ma'am, you add sodium potassium tartrate? No, only sodium hydroxide and that copper sulfate. Sodium potassium tartrate is used as a chelating agent for copper ions while the reaction goes on. This reagent is a very unique and important reagent in the sense that it is not simply used to determine the quality or identify a protein in solution. It too is used to determine the quantity of protein in a given solution. So both qualitative and quantitative assays it fulfills. Uh, 2 ml of the sample solution is taken in a test tube and to it is added 1 ml of 50% sodium hydroxide solution followed by 1 to 2 drops of 1% copper sulfate solution. First of all, sodium hydroxide, 40% sodium hydroxide solution is added and next 1% copper sulfate solution is added. Then it is second well, the tube is second well. Violet color. Look at this. This is the desired color. A dilute solution of egg albumin was first taken in a test tube. 2 ml of the dilute solution, protein solution was taken in this test tube. To it, 1 to 2 drops of sodium, 40% sodium hydroxide was added. The content was second well. Next, 1% copper sulfate solution was added, 1 drop of it, and it was second well. We had this color, and this color is the desired color. We normally get this color, purple, violet purple color. In the quantitative assay of proteins, this much of color is not, we don't get an intense color like this because we extract the protein from the tissue from an unknown source. We don't get it. We just get a faint color that is assayed in a colorimeter or spectrophotometer, then the quantity is determined. This is the color. Did you take it? So, the presence of protein is confirmed. Next, we move on to the qualitative test of a lipid. We have used the coconut oil as the lipid sample. It's a fatty acid, saturated fatty acid, coconut oil. We have used it as a sample. 1 to 2 drops of coconut oil is taken in a test tube as a sample. Then to it, you can do either of the two things. The stain that is used to confirm the presence of a lipid or a fatty acid, as I said a little while ago, to confirm its presence, we use a dye that is Sudan, Sudan, Sudan. It is the name of the dye. Sudan dye is available in 3 forms: Sudan 3, Sudan 4, and Sudan Black B. 3 forms. All the Sudan stain powders are used to make a qualitative assay of any kind of lipid. We have used, what is the Sudan? 3. Here we are using Sudan 3 solution. I am telling you, I will give you 2 options for its use. Sudan powder is commercially available. Sudan stain solution 2 is commercially available. And it's your choice what you will prefer to use. If Sudan powder is used, a few crystals of the Sudan powder is dropped onto the test tube containing the coconut oil. There is no point in stirring it, as soon as the Sudan crystal touches the coconut oil sample, the entire thing turns red or starts turning red. There is nothing to shake it. Usually what we do, we add a reagent, then shake it well for a thorough mixing. But here this is not required. If the dye is, if the solution is used, Sudan 3 solution, it's better. How a Sudan 3 solution is prepared? You take the desired quantity of Sudan 3 stain powder, then mix it in absolute alcohol, a fixed quantity of absolute alcohol. Shake it to mix. It becomes Sudan 3 solution, stain solution. Look at this is the color. Add some more Sudan. A little more, a little more. Just a moment, just a little. That's it. This is the color. Look at this. It sometimes becomes a more intense red color. More intense red color. If a red color develops, then the test sample is confirmed to be a fatty acid or a fat or a lipid. We test for the lipid. So Sudan test for a lipid.